G'day, welcome to our first video for vectors. So we're going to be just an introduction into vectors and notation and that sort of thing today, and just having a look at them. So what is a vector? Well, what isn't a vector is a good place to start. If things are not a vectors, they're called scalars, and they basically just give this scale of something. In other words, what's the size of something? So in other words, this line might be 3 centimeters long or something like that, or I might be traveling at 13 kilometers per hour, or what's another scalar? Scalar might be I'll try to think of another one, but a vector is something that has not only magnitude, so this line here is 3 centimeters long, but a vector also tells you the direction. In other words, I might have this line with an arrow going in it, so it's 3 centimeters. And so the difference between this is the vector has magnitude, it's got 3 centimeters long, but it also has direction, it's going in this direction here. And so they're the difference between the scalar and a vector. A scalar only has magnitude, a vector also has direction, and so a vector in this case might be 13 kilometers per hour. Well, that's not a very good H. Kilometers per hour, maybe east. It's going, you're driving, not only are you doing a magnitude of 13 kilometers per hour, but it's also got a direction, you're traveling in an east direction. So basically that's the difference between scalars and vectors. It's very important to notice this. Because later on, if you get this mucked up, it'll sort of screw you up. So that is how we draw a vector. So we have a starting point, it goes up somewhere, and it goes in some direction, and we have an arrowhead up the top. Okay, oh, not a very good arrowhead, but there we go. An arrowhead like that, and that's it. And it always has a magnitude, a length. That the length determines how long it is, its magnitude, and its direction is where it starts and where it finishes. Okay, so there we go, there is a vector there. Now how we write vectors, if this is the point A and this is the point B up here, then the way we write this vector is A, B, and above it we draw an arrow like that. And be careful that A is the start, B is the end with the arrow on it, just like it is in the diagram here, and not the other way around. So that's how we write it. The other way to write a vector, and it becomes a bit more common when it gets more complicated, is to have, let's call this vector A, so a little a like that. And we call this whole vector A. Here we have a capital A denoting this point, and capital B denotes this point up here, but the small a here actually denotes this actual vector A. And so we often write it like that. And so we don't get confused, so that we know A is not a number or anything algebraic or anything, but it's actually a vector, we actually put a little tilde below it. It's a little squiggly line called a tilde, and we write that below that. So we could write then either way, so it's AB, or we can write that as A with a little tilde below it. And they're the two ways we can write vectors. Now let's talk about equality. When are two vectors equal? Well, let's have a think about it. We've got our line AB there. Let's say that this is 3 centimeters long. So we'll just do 3 centimeters. That's 3 centimeters long. So we draw another line there from C to D. Not a very good D. I'm still getting used to this. And that's 3 centimeters long as well. Now, are these two vectors equal? Well, they have the same magnitude, but they don't have the same direction. So in fact they are not equal. So AB, the vector AB, is not equal to the vector CD. And so that's really important. They have to have, to be vectors to be equal, they have to have both the same length and the same direction. Okay, let's just draw another one. We'll draw another one down here, and I'll try and do it the best I can, try to make them look parallel. And what are we up to? We'll have E, F, and let's say this is still 3 centimeters. Now, I've tried to draw these two parallel, so let's just forgive me for not being terribly accurate, but let's say that they are both parallel. Then in fact they have the same direction, they have the same magnitude, and so therefore AB, the vector AB, is in fact equal to the vector EF. And so they are the same vector. It doesn't matter about position, where it is located. This one's up here, this one's down here. They have the same magnitude, they have the same direction, and so they in fact vectors are equal. And that's all we need to know. If you want to call this vector E, we'll have a little e. Remember to put your tilde down there. Then if we want to write it in the other notation, you can write A is equal to E. In other words, the vector A is equal to the vector E. And that's about it. Let's talk about different ways of writing it. In fact, I'm just going to clear the screen. And do I remember how to do it? Oh, I can't remember how to do it. There's a shortcut, I think. I think I can clear. There we go. Fantastic. The other way we can write it, let's say we've got a some sort of axis here, and let's say we've got a vector going from the origin out to up here, and let's say it goes across 4 and up, say 7, something like that. Then we can write this vector using column vectors. So let's just say that's A and that's B. Then we can write this vector AB as a column vector, like in a matrix here. So, what we say is how far does it go across and how far does it go up. Okay, so how far does it go across? It goes across 4 units. And so we write a 4 up here. And how far does it go up? It goes up 7 units, and so we can write this as a column vector, and that tells us it goes across 4 units, up 7 units. Similarly, if I do one down here, let's just say down to there, just for ease, let's just say that's -3. Then and we'll call this point C. So AC will be equal to, writing it as a column vector. Well, how far does it go across again? It goes across 4. And how far does it go up and down? Well, it goes down -3, so we'll write -3 in there as a column vector. And so that's how we represent vectors in a number of different ways. Now, let's just have a look at what the magnitude is. In other words, the magnitude is how long the line is. How big is this vector? And let's do AB, and well, AC looks very, I've chosen good numbers. Let's do AC just for ease of numbers. We say AC, let's find the magnitude of AC. In other words, what's the length of this line? And we write the magnitude as 2 lines either side of the vector. And that says, how long is this line? So what is it? Well, let's think about it. If you want to know the length of this line, we can just use Pythagoras. And so what is it? The length of that line will be the square root of the horizontal component, so that'll be 4, and Pythagoras said squared, plus the vertical component, so plus 3 squared. And of course we know that's 16 plus 9 squared root of 25, which is 5. So the magnitude of this line here is 5. Similarly, for AB, if we wanted to do the magnitude of AB, always with you over the top, is equal to, what would it be? It would be the square root of 4 squared plus 7 squared. Okay, and that'll give you the length of the line. So that's 16 plus 49, so what's that? 55, 65 square root of 65. I could probably simplify that. 13 times 5. No, we can't. So that's your exact answer there. So the magnitude of that line there is root 65. Fantastic. And the general formula, if you've got some vector, let's just call a little vector A. You've got a vector A which is x, y. Then the magnitude of A will be equal to the square root of x squared plus y squared in general. And so that's how we find the magnitude of any vector. And in fact, I might leave it there and go on to the next vector, because next videos, because I don't want to take too long.